All right, so here is our video focusing on refraction. We will also get into this total internal reflection is something that is part of this video, and thin film interference, going back to our interference talk from the previous couple of videos. Okay, refraction. So we talked about this exact picture before, right? If I've got two little photons right next to each other, right, this photon will come and it will hit. This is a medium where light cannot move as fast. And then this one will come and hit over here. It'll just hit further along. But if light can't move as fast, right, that's just like the analogy was a car with its right wheels on the grass and its left wheels on the pavement. Right wheels on the grass, you can't move as quickly in the grass. So the right side of the car will slow down. Then the left side of the car will keep going, which means the car will then turn. That's refraction. Okay. Oh, sorry. Another thing to notice, just to note, the frequency of light remains constant, which is kind of strange to think about. That the wave slows down, but the frequency remains constant. Um, because if you remember this, velocity equals wavelength times frequency, which for light, remember velocity is c. It's 3 × 10⁸, but that's light through a vacuum. So we get this lambda times frequency, but you can see that right the wavelength gets shorter from each of these. So wavelength definitely got shorter. So if wavelength goes down and velocity goes down, frequency actually has a net no change whatsoever. Okay, so index of refraction. This is this thing called n, this lowercase n. So we've got this index of refraction. What the relationship is actually the index of refraction is whatever velocity you have through that medium. It is c divided by so the speed of light divided by that velocity, which means, right, if going slower than the speed of light, we can never go faster, but if we go slower, that means you have c divided by a number that is smaller than c. So you get these index of refractions from one and one and up. Right? You can never have an index of refraction less than 1 because that means you're going faster than the speed of light, which does not happen. The other thing that this brings about is what's over here on the right side of the screen. N1 V1 equals N2 V2. Right? If you just multiply V across, you get this relationship. And since C is a constant, C is the speed of light, you can say this is true about any two different mediums. Whatever velocity that medium has, and whatever that index of refraction has, multiply those together. That's the same exact thing for the velocity through a different medium and the index of refraction of that other medium. Even furthermore, if we break down the velocity into lambda f, velocity 2, lambda 2, f2, right, the frequency we talked about, frequency stays the same. So this turns into this relationship as well. These things are these two on the right that I can get my highlighter out. These two on the right, this and this, are things that AP doesn't give you, but they do kind of expect you to be able to use and kind of riddle your way through. And know that frequency does cancel out. They do expect you to remember that frequency stays the same. Okay, so speed of light through a couple of different mediums. Air is 3 × 10⁸, which is basically the same as a vacuum. It truly, air has a speed of like 2.998 or something like that, but it's still close enough that we basically just say air is like a vacuum. Ice, and then water, oil, glass, ruby, diamond. Essentially, the more compact the molecules are of a substance, the slower light will travel. The indices of refraction of similar things, right? We have air, we have water, alcohol, glass. Glass is so close to 1.5, we usually just call it 1.5. Oh, my pen is not large enough to see. We usually just call glass 1.5 because it's so close. Plastic and glass are very similar. Diamond 2.42, but water 1.33, glass 1.5. Those are ones that will be used pretty frequently. I'll never expect you to memorize those, and AP will also not expect you to memorize them. Um, but those are the frequent ones, and air, obviously. All right, but then the note down at the bottom that I have for you, the index of refraction for even for the same material is slightly different for different wavelengths, which is pretty cool. Slightly different for different wavelengths. That is why, like, that's why we get rainbows. That's why we get a rainbow, is because the different index of refraction in water for all the different wavelengths means that the red bends a little bit. Red will bend a little bit less. Purple will bend a little bit more. And then everywhere in between for all the colors in between. So that's why we get these rainbows that are pretty awesome. Speaking of which, all right, you know the Pink Floyd logo. Everyone's seen it, whether or not you knew it was attached to Pink Floyd. Red, orange. See if it'll let me get all these colors. Yellow, right? We've got green, blue, and purple. Green, and our blue, and I don't know if I have purple on here. Doesn't look like it. Pink is close enough. Purple-ish. Right, so this is because, right, the white light comes in, and white light is just a combination of absolutely everything. White light is a combination of all the different wavelengths of visible light. So when that comes in, the red light will bend the least, and the purple light will bend the most as it moves through these prisms. One thing that's important about the prism, and we'll talk about this later, if white light hits it at an angle of 90 degrees, if we were to come in at a right angle of 90 degrees, we wouldn't see anything. We would see no reflection at all. But this triangular prism and the fact that we're coming in from over here, that's at some other angle, that's at a different angle, that is what lets us see light breaking down into its multiple different colors. Okay, so here's some vocabulary. We've got our incident ray, right, our incident medium, which in this case, this looks like incident medium is air, and then the refracted medium, just the way it's colored, looks like it's going into water. Refracted ray, and then you get theta R and theta I, theta incident, theta refracted. The normal line just means we make a right angle with whatever the boundary is, and that's the normal line. Because we can use those angles as they're labeled, the ones that are the angle with, excuse me, the angle with the normal line, so that angle and that angle, and we can use a mathematical relationship. And just right, incident medium has some index of refraction of Ni, refracted medium Nr. So those are just our indices of refraction for those two places, those two boundaries. Okay. When something is refracted into a larger index of refraction, right? That means we're going from fast light to slow light, from fast light to slow light. So remember, if we draw our little wave fronts here, all right, so the wave fronts are perpendicular. Oh, my computer screen is not liking me right now. All right, the wave fronts are perpendicular, but this means that that the right side of the wave front is going to hit the slow part first, just like the right tires of a car hitting the slow part first, or hitting the grass. And then the left side keeps going. So the right side hits the slow part first. That means that'll slow down and turn us that way. So then if we take a look at these, right, this keeps going in that first medium just like normal, but now we kind of turn from over there, and now we follow along where this green line is. So this is from air into water. from air into water. The other thing this means is let's say this is you, right? There's your eye, you're happy. Let's say you're just standing there. But let's say let's say we've got a fish down in the water. You see the fish, you will see the fish right here. That is the fish that you see is right there. But the fish is actually down over there. So where you see the fish versus where the fish actually is different because you are looking along this line, you are looking along the red, and that's where the fish appears to be. But where the fish actually is down here. So one thing that's pretty cool is they make some pretty fancy like spearfishing guns that just say how far away are you above the water, and then based on whatever this distance is and the angle, that spear gun can automatically adjust and know to shoot some amount below wherever you aim it at the fish to get it actually to hit the fish, as opposed to hit where you see the fish as being. So that's one of the reasons spearfishing is just so challenging, and why if you ever do try spearfishing, um, get some goggles and put your eyes below the water because then you never have to deal with the indices of refraction, going from air into water. In the opposite way, glass into air, glass into air. So now we're going from, right, n is 1.5 into n is 1.0. So glass into air, right, we have the wave fronts, and we're going from slower, or if it's slower, I should draw them closer together. We're going from slower, which is closer together, until right here. Right here, now you have this. This is basically the right tire of your car is going from grass onto pavement, so it can go faster. So this can now just zip off to the side, whereas this one over here is still stuck in the grass. It's still going slow. So the right side of your car is now going faster. The left side of your car is still slow. So over here, now we will bend in that direction. So glass into air, if you've ever seen like a glass sphere, or if you're looking into a really thick glass window, things aren't where they appear to be because of exactly this. If an object is over here in the glass, and your eye is over here, right, in the air, you will actually see it along this green line. So you would see it, you would see that object right there instead of where it actually is. Okay, but smaller into larger and then larger into smaller. Essentially, if you go from a small angle to a large angle, that means you're going high n into small n, and vice versa. There's an equation that'll help us out with that, that I'll show you in just a moment. But right now, try this out. Which has the higher index? Let's go, just you indicate either A or B for each of these. So A or B. Go ahead and pause the video right now. Try out these 4 problems, and then restart the video, and I'll give you what the answers are. Okay, so hopefully you pause the video. Which one has the higher index of refraction? Well, higher index of refraction basically is where you're going slower. So where we're going slower. I'm looking at this one right here. As we turn this corner, these wave fronts have to speed up, right? The right side of the wave has to speed up. So this is faster. This one is faster down below. We have slower up above. And the higher index of refraction happens where the wave is slower. So that first one is A. All right. How about this top right one over here? A and B. So which one has the higher index of refraction? Well, it's whichever one is moving slower. In this case, it'll be B. Higher index of refraction is whichever one would be slower. This would be slow. And as you come up the other way, oh, I'm sorry, the arrow's pointing the other direction. So this is, we're moving. All of a sudden we turn to the left, which means that the left side got stuck. So the right side kind of came around to help move it. So if the left side got stuck, that means this has the higher index of refraction because we're moving slower. All right, this one over here, I'm hoping that you just see this and you just tilt your head. All right, tilt your head to the right. Higher index of refraction, A, over here, and then over here, higher index of refraction is A as well. So those are the answers to those 4 problems. If you have any questions, definitely let me know. Okay, here's the math I was talking about. So Snell's law is the law of refraction. This is a screenshot from your AP equation sheet. Here's where you can find it. It's on the last page where all the new stuff is. But n1 sine theta 1 equals n2 sine theta 2. All right, and then just a reminder, sine of 0 is 0, sine of 90 is 1. This is actually really, really helpful. And this is how I could do those problems on the previous page so quickly. Because, right, sine of 0 is 0, sine of 90 is 1. So that means as theta increases, sine of theta increases. As theta increases, sine of theta increases. So how I was able to do this is if I know that theta goes down, that tells me that the index of refraction has to go up. So if we look over here, I'll just take a look at this. Right, which one of these has the smaller angle to the normal line between theta of A and theta of B? Which one's the smaller angle? Theta of A. All right, because we have N1, or I should say NA sine theta A, and then this one NB sine theta B. And we know that as both of those have to be equal, so whichever one has the small angle has the large index of refraction. And that's how I was able to get those answers very quickly. Small angle means high index of refraction. Okay, let's try this out though. So find the angle of refraction as we go from air into water, and let's say we start at 45 degrees. By the way, that's the index of refraction, our refracted angle. That's what we're trying to find. Okay, so we just plug into this equation here, n1 sine theta 1, n2 sine theta 2. So n1, that's air, so right, we have 1. And then sine of 45 degrees is where we start. n2, 1.33 times sine of whatever our refracted angle is. Okay, so I can get sine of theta r. If I plug in sine of 45 degrees, that spits out 0.707, then divide by 1.33. So I get sine of theta r is 0.532. All right, then you take the inverse sine of both sides. So theta is the inverse sine of 0.532. So I want the inverse sine of 0.532, and that spits out for me, that gives me 32.1 degrees. Okay, so 32.1 degrees, which makes sense because it is smaller than 45. All right, so remember, bigger N, smaller angle. One more problem here. So between air and glass, right, we start at 20. What's our refracted angle? That's the question for you. So same exact process. Go ahead and pause the video, see if you can do this on your own before I keep going. Okay, hopefully you paused. I get 1 times sine of 20 equals 1.49 sine of theta 2. And here, theta 2, then if we do all this, inverse sine of the sine of 20 divided by 1.49, 13.3. Is that right? So I got 13.3 degrees, which does not make sense to me because Oh, that's because we started in glass. I apologize. Um, I'm glad I checked to see if that made sense. Just so you know, I got 13.3 degrees when I did this, but that doesn't make sense because that would have meant going this way. But my mistake was I thought we were going from air into glass. We are not. We are going from glass into air. So N1 is actually going to be 1.49. My apologies. Sine of 20 equals N2 is 1. Sine of theta 2. Sine of theta 2. Okay, so theta 2, I get, let's see. That makes more sense. Now I get 30.6 degrees. 30.6 degrees in the air. Okay. Let's say light travels from air into another substance. So we've got air into something. That's my normal line. I should do this dash line. That's the normal line. I have light from here, and it comes in at 20 degrees, and it comes out, theta refracted, at theta 2 is 8.12 degrees. Okay, what is the substance? And I give you a list of a bunch of different things here. So we know that it has to, air is 1, sine of theta 1, which theta 1 is 20 degrees. And then theta 2, we don't know N2, we don't know what that is, but then sine of 8.12 degrees. Okay, so this tells me N2, if I take sine of 20 divided by the sine of 8.12, I get N of 2.42. Oh, hey, look at that. Diamond it is. That's one way that you can identify an unknown material. Is you can plug it in and find put in a known angle of refraction from a known substance, measure the angle out, and then you can find out what the index of refraction is. That's one way we can help ourselves learn what substance something is. Oh, by the way, units on this, they are unitless, because it's just a ratio of how closely compacted are the molecules compared to a vacuum. So it's just a ratio. So n indices of refraction are unitless. I have this little slide in here which basically tells me if I go from one substance to the same substance, I'm just going to go straight, which is really pretty straightforward. So I won't spend any extra time there. Another example of Snell's law, and this is something that you might get. If we were to run through this example problem right here, find the angle of refraction for a ray in diamond incident upon air. So we have diamond, n equals 2.42, incident on air, n equals 1, at an angle of 30 degrees with respect to the normal. So if we get 30 degrees to the normal, 30 degrees with respect to the normal, figure out, all right, this is air, so it's gonna be a steeper angle. What's this theta? Well, if you plug everything in, you get inverse sine of 1.21, which is not allowed, right? Sine can only be between 0 and 1. So if we're having to take the inverse sine of something that's greater than 1, your calculator would spit out domain error. What domain error means is that sorry, my alarm went off. This means that would actually go backwards. You'd get an angle greater than 90 degrees, which doesn't really happen. So that doesn't truly happen. What does happen is this thing called total internal reflection. the total internal reflection. What this means is no light passes through. Right, so this is from water into air. It gives you all these different values. So if your angle is 0, then sine of theta, sine of 0 is 0. So you just go out, you go straight through. Whereas 20 degrees, you'd come out into air at 27 degrees. 30 degrees, you come out at 42, 40 to 59. This is the critical angle right here. So that critical angle, you come in at 48.8 degrees. And if you do the math for Snell's law, that would spit out exactly 90 degrees. Well, what that means is after that, after you spit out 90 degrees, what happens if you get even more shallow? It would have to go past. It would have to go past that number right there. So then you actually get a reflection. So Snell's law no longer works. Snell's law just does not work, and you get this reflection here. This is called total internal reflection when you can't, when no light escapes. No light escapes whatsoever. If you've ever bent down kind of on the side of a fish tank, you've seen this. Because you cannot see through the water, you cannot see through the glass. You get this total internal reflection. Now you have to be at a pretty good angle, pretty shallow to wherever the medium is, because you want your incident angle to be fairly large. The larger your incident angle, the more likely you are to get this total internal reflection. We can see it like this. All right, so we have this laser coming in from the right side. This is just a red laser. The laser, if it pointed straight, would follow right along this line right there. That's the dashed line I have for you. But when it hits the boundary, right, this boundary, I can only assume this is glass. When it hits the boundary, right, it goes across this. Right, that's the line that's perpendicular. So we have theta incident and we have theta refracted. But then when we come across to the other side up here, now we have this boundary. That's the normal because that's the boundary. So this boundary, we have this new boundary. We have theta incident, so theta refracted. Theta refracted, you would expect somewhere up there, but if you were to do the math and know what the indices of refraction are, you'd get a domain error when you try to take sine of or inverse sine of whatever it is. If you ever get domain error, that means it is no longer refracted, it is reflected. You cannot have any light pass through, but you get a reflection. So what we get here instead actually is, now if we do this, we get theta reflected. And one thing that we can always know about reflected rays is that the angle incident is equal to the angle of reflection. All right, so we've got refraction and reflection. Refraction, you use Snell's law. Reflection, the angles have to be equal. This total internal reflection is really cool for uses. I was getting ahead of myself there. This critical angle, that's whenever you get the inverse sine of 1, right? So that gives you 90 degrees. Critical angle is whatever angle makes it so that you spit out a 90 degrees as your other angle. This only happens when you go from high into low. From high index of refraction into low index of refraction. It only will ever happen there. The angle of incidence, this is the angle of incidence when light can no longer be refracted and at which total internal reflection occurs. As far as why it's only from high into low, right, if we go n1 sine theta 1 equals n2 sine theta 2, let's say n1 is greater than n2. N1 is greater than n2. So going from high to low means we have to go from 1 into 2. So we'll start at 1, but that means we want theta 2 for the critical angle. We want theta 2 to be 90 degrees. Okay, so 90 degrees, that gives us 1, which means sine of theta 1 has to equal n2 over n1. We can only ever go, this can only ever be impossible. Like you will only ever get a number that is impossible to calculate when this is greater than 1. When that is greater than 1. Okay. Oh, no, I'm sorry. You only get a number that is possible to calculate when that is less than 1. That's how we know. I'm sorry. I was mixing myself up. So that has to be less than 1. Oh, sorry. This has to be less than 1 for this to be possible. If this was greater than 1, it would be impossible, and we would not have this critical angle. That means you could never reach 90 degrees, is if this was greater than 1. So we know that n1 must be greater than n2 for this to be possible. So you have to start from a high index and go into a low. When you get something like this, when you have a small enough, or I should say a large enough incident angle, when you get that number, then you get this phenomenon called total internal reflection. So that's when you can't see anything else past that boundary. This is really useful for something called fiber optics. Fiber optics, right? Most of these, you get a bright spot right at the very end. Bright spot right at the very end of all these little cables, but most of the way through, right, you can see there's not much light. There is a little, and that's due to this thing called electron tunneling, which is a Unit 7 topic. But pretty much, you get almost no energy loss, which is really awesome. No energy loss. And that's why if you have Wi-Fi that is built on fiber optics, it is so much better than Wi-Fi built on just normal cables. Okay, calculating critical angle. I kind of went through this. You just have to assume that sine of 90 degrees happens for the other one. So you just go through and you take the inverse sine of all these things. That'll give you the critical angle. And remember, this has to be less than 1 for this calculation to be possible. If this is ever greater than 1, that would mean that the refracted angle would be greater than the incident angle, or index of refraction would have to be greater than your incident index of refraction. If that was ever greater than 1, this would be impossible, which means you couldn't have a critical angle. So you have to have your incident must be greater than your refracted to get this internal reflection. Okay, so this just reaffirms all this. I'll let you, if you want to take a look at this math, pause the video, look at this. But this will show you critical angle and what's possible versus what's impossible for critical angle. By the way, AP does not ever give you this. They just expect you to be able to know how to do it from Snell's law, which is, it's not bad. It's right here. You just plug in sine 90, and then you can work it all out from there. Okay. This also tells us why diamonds are so pretty. Right, diamonds are spectacular to look at because they look like they have all the colors contained within one little gem, which is basically true. We were talking earlier about, right, different wavelengths have different indices of refraction, which means they will have different angles, right? At Snell's law, n1 sine theta 1 equals n2 sine theta 2. If they have different indices of refraction, that means they'll have different angles that they come out at. So that's why we get all the different colors from this. And I'm just now realizing that this is missing orange in this picture. There we go. We'll add orange back in. So it's missing orange. But we get these total internal reflections because diamond has such a high index of refraction that when we go from when we're trying to go from high to low, from diamond to air, It really does not take a lot to get through or to get this total internal reflection, because we go from such a high index of refraction down to 1. So diamonds are really pretty because of that. Okay, got one other thing. This kind of goes back to our interference that we did before, but you had to know how to do refraction for this. So this is something called a thin film interference. Thin film interference. There aren't a ton of questions about this, but you do have to know thin film interference to answer a couple of the questions. So let's say there's an incident ray on just a really thin piece of material. And by really thin, I mean like on the nanometer scale. Nanometers, sometimes micrometers if you get lucky, but typically nanometers. This thin film interference. All right, so we have light coming in. This light is our incident light. When it hits a boundary, this is actually what we hadn't talked about before. When light hits a boundary, some of that light gets reflected and some of the light gets transmitted. That's just true of any time light hits a boundary. Some gets reflected, some gets transmitted. The reflected light, right, that just goes off, and then the transmitted light comes back down. But now we have the other side of the film. So again, some gets reflected, some gets transmitted. So we have this transmitted light that goes all the way through whatever gets transmitted at both sides. Then the reflected light from back up here, right, that goes up. Some of that will get transmitted, some of it will get reflected. Same thing's going to be true down here. When we hit that point, some reflected, some transmitted. Up here, some reflected, some transmitted. Down here, some reflected, some transmitted. And that just goes on and on forever until that gets to be low enough intensities that you can't even see it. Okay, but we can use this with interference, right? Our constructive versus destructive interference, which is kind of cool. Because when you go from, and I have this over here, when you go from a low index of refraction to a high index of refraction, on that reflection, your wave actually gets shifted by 180 degrees, which is half of a wavelength. Then when you go from a high index of refraction to a low index of refraction, there's no shift in wavelength. As far as reflected things go. So when you go from low end to high end, we get this phase shift of essentially half a wavelength. And when we go from high end to low end, there's no shift. It just continues being exactly the wave it was before. What that looks like is if I were to take this. Let's take the black pen. Here we go. If we go from high to low, right, there's no shift. So it'll just do this, and then it'll just keep going the way it was. So it comes in here, and then it'll just keep going the way it was. But if we go from low to high, what ends up happening is it comes in here, and then it gets reflected back the way it came. That's from low to high. And this is just for electromagnetic waves. It doesn't make a lot of sense for any other type of transverse wave. But high to low, it just keeps doing exactly what it would have before. As opposed to low to high, it gets reflected back in the other direction than it was coming from, which is just strange. So what that looks like is if we were to take a thin film with a thickness of half of a wavelength, that means that whatever this is coming from, so that means that this has a wavelength of lambda over 2. So in the time it takes our wave to travel down and then back up, So travel down and back up. That means it's gone an extra path length of lambda. So that means we would normally expect this, okay, if that's the wave right there, we would expect it to do the same thing. And then, right, they're in phase with each other, so we get this constructive interference, right? The peaks and the troughs are at the same place, so you'd get this constructive interference. But that's not true because that one doesn't just reflect where it is. As we go from a low index of refraction to a high index of refraction, and I say N2 is greater than N1, that means that this one gets reflected. So we get right here, we get this trough and this peak. What do troughs and peaks do? They cancel for 0. We get this peak and this trough. What do those do? They cancel for 0. So we can get this thin film interference if our film is I'll fill those back in. If our film is a thickness of lambda over 2, that means we will get destructive interference almost everywhere. Destructive interference almost everywhere. So lambda over 2, destructive, which means we'll have just an intensity of 0. We cannot see the light. As opposed to, what if our thickness is lambda over 4? What if thickness is lambda over 4? Then that means this is not a lambda difference. When it travels down the pathway and up the pathway, we get a lambda over 2 difference. Okay, so lambda over 2. So this is just our normal wave exactly as we expected it. So here's our normal wave as we expect it. And this one, right, we would normally expect it like that, except what would happen? I'm sorry. I'm going to back up for just a moment. Backing up for a moment here. This is not as we expected there because it's only gone lambda over 2. So that means it'll start right there. So I'm going to back up and that will start in that way, actually. All right, then how about our incident one? If this is what we normally expect, but remember we go from low to high index of refraction. So when we go from low to high, what does this do? It doesn't go as we expect. It does that 90-degree shift, or 180-degree shift, that lambda over 2 shift. So what we see then, trough and trough, those will match up with each other. Peak and peak, those will match up with each other. So we will get this constructive interference. So when we have a thickness of lambda over 4, we get constructive interference on this thin film. This is something that I don't see too often on the AP question bank, but it's there, and I just wanted you to know, right? Lambda over 4, constructive. Lambda over 2, destructive. And this is true of essentially any integer of lambda over 4. So you can get lambda over 4, 3 lambda over 4, 5 lambda over 4. But then any multiple of lambda over 2 will give us destructive interference. All right, I've talked at you long enough now. I'll stop this video. If you have questions on this, let me know.